That's going. Okay, tonight we're doing module 5 and 6, and I don't think we'll need the whole hour because this should be sort of a review. As we talked about before, you really can't do cybersecurity without networking. In fact, I've been talking to several groups lately about some of the technician pathways that are available now in Network Academy, specifically the Cisco Certified Support Technician in networking, and then there's one in cybersecurity, and then there's one in IT support. And when I show the pathways, there's many more hours in the cybersecurity pathway because you have to take those networking courses. But the CyberOps class does have a little bit of review on networking. So we'll do a little bit of that today and a little bit more next week. And they're not long modules, and a lot of this should be very familiar to you. I'm not going to just read everything to you. Most of this is pretty obvious. So, you know, there's different kinds of networks and different sizes of networks around, and you will see questions at the still about small office, home office networks. You know, a lot of us work from home. I know I do, and seems like the longer I'm here, the more stuff I have around me to make sure that I have everything that I need. Client-server communications, you know, is part of the network protocol section. Clients have software installed that they request information obtained from the server farms out that information. Client-server communication, of course, is just has files in a central location many times. This is a familiar topology. Web server runs web server software. Email server runs client software. And the communication protocols, I know with students, a lot of time when we talk about the word protocol, and you all could probably give me a good lesson on this, it's hard to explain to students what a protocol is. A protocol is simply a piece of paper, a rule, if you will. A protocol has to be more or less standardized for communication to take place on networks. And those network protocols, they do all that encoding and formatting and encapsulation, etc. Lots of different networking protocols. We'll refer to a few of them tonight. They do use a structure. So here's the host sending a message, and that message contains an IPv4 header, and the router understands that because of the header. And yes, sir.
I just wanted to double check because of the way you said something. You're not sharing a screen, are you?
Oh, yes, I'm sorry. I should be.
Okay. You sounded like you were, so I just wanted to double check.
Yeah, I guess it went off for some reason. Yes, I am sharing the screen. I apologize. Thank you so much for telling me. I could have talked this whole hour and y'all would have been asleep and never known that I was sharing something.
No. I want to let you know I'm paying attention.
Oh, I appreciate that very much. I apologize for that.
No problem.
We're just talking about protocols, communication protocols. Evidently, I clicked stop up there and didn't recognize it. So there's a whole process of this. This is in the networking course. A lot of this is in the networking course that you all took early. So we won't go into a lot of this. We do, however, want to talk a little bit about the TCP/IP protocol suite. Extremely important when we talk about cyber ops or network security. That TCP/IP, as well as the OSI layer. And if we break it down, some of the very important ones, we know ARP is used to find the IP address that goes with the MAC address of a host. And you cannot communicate with a host via IP until that source has a corresponding IP address and MAC address. It's the only way you can communicate. DHCP v4 dynamically assigns IP addresses to endpoints. I think you all know what DHCP is. DHCP v6, which we didn't really cover in the networking course. DHCP v6 can be you can have a DHCP v6 server that will farm out both an address within a range of addresses as well as the gateway and other specifications. DHCP. DNS, resolves names to IP addresses. That's just a few. There are a lot, and many of them that you will do in your labs are going to be here in this transport layer. Here's some other protocols. I think most of you are familiar somewhat with these. There are some questions on the CyberOps certification, like for instance, what's the difference in SMTP and POP3? And you have to know that POP3, clients retrieve mail from a mail server and download the email to the client's local mail application. So there's a fine line difference in some of that. I'm sorry, POP3 and IMAP, excuse me. Then HTTP is the hypertext transfer protocol, and then the secure HTTPS. That's REST is a web service that uses application interfaces or APIs. Transport layer is comprised of two protocols. TCP is transmission control protocol, under which there are many protocols. That is the reliable communication between processes. Reliable, there is confirmation. I'm checking to see if you got it. Here's a sequence number. Here's my next sequence number. UDP, it just says, here it is, hope you get it, I'm not checking. So some protocols use both TCP and UDP. Again, as a review, within that internet layer, you have IPv4 and IPv6. You also have NAT that translates IPv4 to to private IPv4 to globally routable addresses for public routing. There really isn't a NAT for v6. Or there could be one, but it's not going to be used probably. I say that and then it probably will be. There's an ICMP v4 for IPv4, and there's an ICMP for v6. And then there's a neighbor discovery for ICMP. And that's when a peer discovers its peer address using that link local address. That is a special kind of IPv6. There's also a router discovery, other types of packets that are discovering while the router advertises also. OSPF is one routing protocol. We do that in the third course for CCNA. EIGRP used to be a proprietary to Cisco. Cisco opened it up, but it doesn't really have all the enhancements that the Cisco EIGRP has. BGP is on another open standard, as is OSPF. It's used mostly between internet service providers. So there's also, just as we said before, address resolution provides the dynamic addressing mapping between IPv4 and the hardware, the MAC address. And there's Ethernet rules for routing and signaling, and then wireless LAN as well. Of course, when a message is sent from source to destination, there has to be a format. The curriculum goes into that, as did the first networking course. So you might want to review that in this module. I didn't include a lot of that. The conversation is about how the messages are formatted. Here's a little bit, and they give you the analogy of writing a letter. Correct format is required. If you put the wrong address on it, or if you put it in the wrong place, it probably won't get there. So the message formatting has to be, that message has to be formatted. There is many times a beginning of frame and an end of frame. Similar to sending a letter, that message is sent over a computer network and it follows a specific form. Actually, the IPv6 header is much less complicated than the IPv4. But IP sends a message from the message source to the destination over one or more networks. And this is just the analogy of communication. And I think you all have seen this analogy before. There has to be encoding between hosts. It has to be suitable for that medium, whether it is Ethernet, HDLC, wireless, and has to be formatted to be able to travel over that medium. Flow control takes place at both the second and third layer in the OSI layer. How much can be sent? What speed can it be sent at? Is there a timeout? And also, for instance, here on access method determines when someone can send a message. Way back when we had the, I remember years ago, I taught off a, see, what was it? Yeah, I don't remember. It was a token ring network where in order to send a packet from your computer, you had to wait for the token in a ring. Any of you familiar with token ring networks?
Yeah.
Hopefully somebody is.
My first military network was token ring.
Yeah,
All right. Yay. Somebody
yeah.
remembers.
We took apart the token ring network at Wilmington Trust. My
Wow.
former job.
That was a service you gave those people by taking that thing apart.
Yeah, we had to replace all those BNC connections with Ethernet.
Oh, I hate those things.
Yeah.
And the T connectors always, you know, you had to unscrew them, do them again because they always messed up.
Yeah, or we had the problem where people would steal the terminator. All of a sudden the network would stop working.
Well, those were the days.
Yeah.
Those were the days.
Larry has no idea what we're talking about.
Well, that's okay. You know what? He knows a lot of stuff we don't know.
He knows a lot more about juice than we know. So.
Oh yeah, that's right. Let's see. I think there we go. And as far as Ethernet goes, or as far as IPv4 goes, there's a unicast and there's a multicast and a broadcast. Broadcast, there is no broadcast with IPv6. Multicast is when you've got a one-to-many, kind of like I'm doing right now, one-to-many. Unicast, one-to-one. I dial your phone, and that's a unicast. The layered model is what we use, and Cisco really is heavy on the OSI. We did this in the first course. Hopefully you remember all of this. Again, there's some of the protocols that are used at the different layers. Note that the internet layer on TCP/IP model relates to the network layer on the OSI. They lump data link and physical in with the network access on the TCP/IP. Transport is transport, and application is the top three. And this is really important that we understand this. This was when we did the first course, when we did the ITN course, we talked about this, and hopefully you all know some kind of sentence that helps you memorize what those different OSI model layers are. Like I said, the TCP/IP protocol model is referred to as the internet model. And there's the TCP/IP. Again, there's just 4 layers on it versus the 7 layers of OSI. And you'll get questions. If you take the CyberOps cert, you'll get questions on both of them. So if there's a lot to send, what happens is there has to be some kind of segmentation that takes place. And that data has to be divided into smaller units. There has to be something to keep track of all that. This does speed up things when you divide that large stream of data into packets, and it won't tie things up and supposedly increase efficiency. Because if only one part has to be retransmitted, it would be much quicker than the entire packet being retransmitted. And this is just a picture. This is from the curriculum. You've probably already seen this. TCP is really important in the transport control protocol because he keeps track of the sequencing. And I believe there's a good explanation in this, and there is a good explanation in the ITN course. If you can still get to your ITN course. Protocol data units, those are PDUs for short. They are, if a protocol data unit, which is an application PDU, is passed down the protocol stack, it has to be encapsulated, changed as it goes down the stack, and we'll look at a demo of that in just a few moments. And what happens is this application data, as it goes down the OSI, as it travels down, each layer beneath will encapsulate it in whatever protocol that particular layer is used. And there's a different name for that all the way as it goes down that OSI. And these are really important that we know this. Data is what's at the application layer. That's the data. That's the web page. That's the data. And as it's passed down to the transport layer, it is segmented. As it's passed down to the network layer, it becomes a packet and it becomes a network layer PDU. And that entire packet is then framed at the data link layer and in turn sent over that physical layer, transmitting by ones and zeros across whatever medium it is. So we encapsulate as we go top to bottom. We de-encapsulate as we go from bottom up. So you get it, you get the entire frame, if you will, here, and it has to be, as it's passed up to on the physical layer, as it's passed up, the data link layer is comprised of that MAC address, and that's removed basically, so the network layer is seen. Sometimes if we're going between switches, the only thing we're going to be using is that data link layer, the MAC address. And as I just pointed out, here's the electrical frequency or radio frequency signals. This is the medium or physical. And then it goes up to the data link, which is the MAC address. There's the network, both source and destination, depending on whether you're encapsulating or decapsulating. There's an example. So let me stop just a moment and bring up just a simple little demo that would illustrate this. So I have a client here, and I've got this guy over here set up as a web server and a DNS server and a FTP server. So if I want to, first of all, just ping over there, move this out of the way, make sure we're connected. I'm going to open up the simulation down here at the top, bottom right, so we can see what happens here. I'm going to show all the filters. Let me edit them. Show all none. I'm going to edit. Right now, I just want to see ARP and ICMP. Let me just take them all out. And then I'm going to add ICMP and ARP. I think we did something similar to this earlier in the ITN course, but we're going to add to it tonight. So right now, the only thing I want, the only protocols I want to see are ARP and ICMP. As I'm going to ping from the client to the server over here, just to see for connectivity. So I'm going to ping it 10.0.0.1. We'll start the ping. I'm going to come over here to the right and start the process. It didn't do the, okay. Wonder why we, oh, because I have none. Huh, it's interesting. There we go. We'll look retro after the fact. So what happened was an ICMP packet was prepared, and because I was pinging an IP address, that packet was being prepared at layer 3. So at layer 3 on the client, the source is 10.0.0.2. It was going to 10.0.0.1. So it's starting the ping process. So it creates this message, echo request message, and it sends it to the lower process. So if the source IP address is not specified, so it sets it to the client. So if I go to the next layer, notice now how it passes that information down. It is a unicast because we're trying to ping from 10.0.0.2 to 10.0.0.1. The ARP process has to look it up in the ARP table, but it's not in the ARP table. So right away, what happens is we forget the ICMP packet. If we go next layer here, we're not going to get anything. So that they forget about that ICMP packet, and that ARP packet is prepared at layer 2. There's layer 2. There's the MAC address for this 10.0.0.2, and he's going to send a broadcast MAC address to from the source to the destination. We could have some intervening devices here, but we just have this one place. The ARP process constructs a request for the target IP address. Now it encapsulates that protocol data unit into an Ethernet frame, and it sends out the frame. And that's all we have on that particular one. We're over here at server 0. He receives it on the frame, fast Ethernet 0. He receives it. He passes it up. He starts encapsulating it up, and he sees that he's got it from 10.0.0. Whoops, I think I skipped one here. Yeah, let me do this one. Yeah, this is what I wanted to show you. So we're at server 0, and he received it. When we go up to the next layer, we see that he got a broadcast MAC address. So he's asking if his IP address 10.0.0.1, that is the destination this client is interested in, is that him? And he says, yes, it's me, and I'm going to replace that all F's with myself, this 8A1C, and I'm going to send it back to you so you'll have my ARP address. So then we go down the layer, and it sends out the frame. And that happens several times. We have to ARP a few times before we can get that in there. When this client finally understands and knows that that particular address is going to be in its ARP table, then it can stop preparing ARP packets and go back to preparing that original ICMP packet. But this time, he knows he has in his ARP table an IP address that matches that 00D0. So he sends it out. And then if we go to the next one, we're at the server 0 now, at the server 0. And he receives it. He's trying to, the frame's MAC address matches the receiving port. That's me. It decapsulates it from the Ethernet frame. It decapsulates it, passes up. Now, finally, layer 3 can get involved. Couldn't get involved until we had ARP table existing on the client. We can look at the PDU, that protocol data unit details here, and see more information if we'd like to. Notice there's a sequence number here, and there's the data. So now, if we want to look at, right now, all we did was look at those bottom 3 layers. If we want to look at it, go all the way up to the application layer, we're going to have to use the application layer protocol. So I'm going to clear this. Clear it here.
Can I just ask a quick question?
Please.
So you're saying, and this, my last CCNA class was well over 10 years ago. So I guess I want to understand. So once that communication has been established between the client and the sender and the recipient, does the communication change, or do they just keep sending the encapsulated packet the same?
Oh, okay. Well, the packet that I was sending was an ICMP echo request with a ping. So
Right.
once that is satisfied over here, so after we pinged it, bring it up over here on the left,
Then the
and
packet changes.
And we got result after we pinged it and we got results, and go back to real time, then that task was complete.
Okay. I was just trying to understand like what happens after the client knows that on switch number, blah, 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 port number, blah, 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 this is where I find my recipient that I've now established communication with. Is that kind of what's happening, or no? Is it just still, is that all that happening within each packet?
Yeah, you mean when we examine the protocol data, when we examine the OSI, that happens every time anything's sent. So let's do another one.
Okay.
Let's do a HTTP packet. Okay. So let's do and I'm not sure I'm answering your question, but let's see if this does. This time let's do here we go. I know it's alphabetical. This time, let's open the client and let's go to the browser. And let's, so we're in simulation. And let's go to the IP address. I think I might have a DNS entry for it, but we'll just play it safe and just go to 001. And I'm gonna hit go and start the simulation here and stop it. And let's look at the packet. And if this doesn't answer your question, be sure and tell me. So here we are at the client. We're going to start at the application layer, HTTPS. So we're going to start up here. There's a lot that takes place at the session layer that really the simulator is not able to show. The session layer is one of those mysteries of life. Not a lot of people talk about it, but there's a lot that goes on in the session layer. This is the presentation layer. So right away, the HTTP client sends the HTTP request. So what are we wanting? We're wanting a web page, right? Because we're trying to connect to our web server. So we're wanting a web page. So if I go to the next layer, notice now layer 4 is also involved. And the reason layer 4 is involved is because of the TCP port, which happens to be 443, which is HTTPS. This is some random port that is used by the source, but the destination is what we look at because that's the HTTP port. So we go from what the user sees, HTTPS layer 7 application, to the TCP port. And then if we go down, and there we've got the segment information we talked about. There's sequence number 1. There's an acknowledgement number 1. The data length is 97. We go down a layer. Destination IP address is in the same subnet. That's a no-brainer. Passes down to Ethernet. It's going to encapsulate it further, and it'll send the frame. We go to the next packet. Okay, I've got to let it. Well, I've got to let the simulation play a little bit here. Okay, let me stop it and go here. So now we're at the server over here on the other side. The server receives that request, which is in the form of a TCP packet, which happens to be a HTTPS packet or port or application 443. It passes it up. It passes it up to the layer 2. Then it goes to layer 3. Now we see that it came from 1025, so that has a lot to do with the sequencing because it's got to know where to send it back. Destination is itself 443, passes it up to HTTPS, and then the next layer that's the in layer. If we look at the inbound PDU, there's some information. There's the preamble we won't talk about. There's the destination address, source address, MAC stuff, all MAC stuff. We get down here and we've got the source IP. This is the part of the IPv4 header, which we won't discuss tonight. Then we get the IP stuff. There's the data. There's the web page. And now the source port is 1025 of the original source port going to 443. There's some sequencing and acknowledging take place as well. We'll go to the next layer. Now that web page is going to be sent back. And you see the picture over here on the left. It's going to be sent back. And as it goes down, the source is still 443 HTTPS. Destination, we know it's 1025 from the client and so forth. Now, did I answer your question?
I think so. Yeah, I was trying to understand where that established communication happened. Did it happen on layer 1 and 2? Or did it happen on the higher layers? And it sounds like it's still happening on
I'll
the higher
give you
layers.
a good Eastern answer. Yes. Never mind. Well, the session layer actually is really what's taking place a lot is the session layer, layer 5 here. But TCP keeps track of the conversation by the sequence numbers.
Yeah, I was just trying to understand who established that level of communication that said A is talking to B.
TCP
yeah.
protocol establishes that communication.
Right.
Anybody else have comments? Okay. All right, let's just do one other. Close this down. Let's do one other. Let's see, let's show, take them all off. We'll do FTP packet. It's going to be kind of the same thing. So I'm going to open the command prompt. I'm going to do FTP to 10.0.0.1. Start the simulation. Wow, it connected really quick, didn't it? But it's very similar to HTTPS because it's going to be a layer 7 or application layer protocol. And now notice the source port. Yeah, I should have clicked up here. The destination port is 1026, because when we're coming back the other way. And there I've got username there. I believe I've got it set up as Berryman. Have to stop and start this. I get the password. FTP is not the best simulation on Packet Tracer. You have to stop it and start it a good bit. So then I can put whatever I want to put. And we could look at those packets, but it's basically there's just transferring up and down, transferring that FTP, using the FT protocol to transfer the file. That's why I like Packet Tracer. You can see how many steps it really takes. If we're doing this live, it happens so quickly, we can't really see what's going on. And I don't think we've got it yet. There we go, it did transfer. So if I look at the web server under FTP, I should see a file called sample.txt, and there it is. Okay. Okay, so that's just a little demo on that encapsulation and de-encapsulation. Module 6 is Ethernet and IP. Again, we went over most of this in the first course. I don't know that all of you were in that course. If you were not in the course and you're going to go further with CyberOps, I would recommend highly that you go on our NetAcad site and take Networking Essentials. Show you where that is. So you all have a login, and you can go in to NetAcad, and if you go, so you're going to have to go to My Learning, which you do for this class anyway. And let's see if we can find. Okay, there's a Networking Essentials course that you can enroll in and take. You can take you can take the self-paced version if you'd like to, and it gives you everything that I've just talked about. Is going to cover a little bit better than what I just covered about. There's the network segmentation and the addressing formats and so forth. So if you have not taken a network course, you might want to review it a little bit. We're just going to go through this pretty quick. We already talked about encapsulation and framing. There's the Ethernet frame fields. It's usually 64 bytes and goes up to 1518. There is a frame check sequence. Also a preamble, start a frame. Used to, when we taught networking, we looked at that preamble pretty closely. They've taken a lot of that out now, and we don't do that as much. Got to have the MAC address, and there's 3 different ways you can write the MAC address: with dashes, with colons, or in 4 digits at once, representing the MAC address. If you're not familiar with the MAC address and a little bit about hexadecimal, then again, you probably need to look at that networking course. That's the network layer. We already covered some of this. That's where addressing takes place as far as IP. And the network layer encapsulates that protocol data from the transport. The transport is going to hand down that PDU, and it changes that segment. There's a transport segment into a packet, and then it passes it down to the data link. Let's go on. It is connectionless. IP is connectionless. Best effort is not guaranteed, but it doesn't matter what kind of media. It can use whatever media is present. And there's some analogies you can look at in the curriculum, but the big thing is IP protocol does not guarantee that all packets will be received. That's what it has to rely on the transport layer for. The transport is the guarantee. I'm not going to do IP addressing basics. If you are not familiar with IP addressing, you need to learn the basics. There's plenty of just very basics in this module. I would recommend, if you are not real familiar with IPv4, and I really don't know you, most of you probably are familiar with it, but if you're not, again, I recommend that you look at that Networking Essentials course. Hopefully this looks familiar to all of you. You've had to change your IP address or check it at some point. And the subnet mask is used to determine the actual network address of that device. So the network address here, the IP address is 192.168.10.10. And what happens is the subnet mask, which is really all ones, 255, all ones, is 255, all ones here, is ANDed with the host address in order to find out the network address. And I believe it tells us that on the next screen. So there's the IPv4 address, 192 in binary, 168 in binary, 10 in binary. Host portion this is the binary address for 10. And the subnet mask is all ones for 255 and a 0 here. And what happens is, I guess I took that out. What happens is that we are ANDing that host address with a subnet mask. And the only time a 1 is returned is if both positions are ones. So everything else is a 0. So if we AND this address with a 0, then it's going to return zeros. That's 8 zeros here. 8 zeros is going to return 0, and that tells us the network address then is 192.168.10.0, and that's the process of ANDing. There's the different prefix links for subnetting. These you should, if you teach networking, you know these in your sleep, backwards and forwards. There's the logical ANDing operation. A 1 and a 1 always returns a 1. A 0 and a 1 is a 0. Everything else is a 0 except a 1 and a 1. There's what I was trying to show just a few minutes ago. I'd forgotten this was in here. There's the subnet mask. And when you AND this number with this zeros, you get a 0, and that tells us the network address. Lots of questions on the CCNA about this still. You still have to know how to get the network address given a host address in a subnet mask. Why is very important. This host here has to know where to send a packet in order to be routed. So if this host wants to get to the remote host, he has to go through his default gateway, typically a router port that is part of his LAN, and that has to be configured on the PC, the gateway. A default gateway is a router that has a local IP address in the same address range as the other hosts, and it can accept that data and then forward it out of the network and route it to other networks. Default gateway is required. If it's DHC, if you're using DHCP, that default gateway can be farmed out to the host. You don't have to configure them individually, of course. You can do this on your PC and actually get a routing table on your PC. IPv6 is 128 bits versus a 32-bit IPv4. If you are not familiar with that, you need to review this chapter a little bit. Again, I'd refer you to Networking Essentials if you need to look at it. So 4 hexadecimal digits is equal to 16 binary digits. We used to call these nibbles a long time ago. There's examples of IPv6 addresses. These is also an IPv6 address. This would be a link local address, which is kind of like the Microsoft 169 address used on a PC if there is, if you're on just a LAN that is within a classroom. As far as writing an IPv6 address, you can omit a leading 0, or if that particular hextet is all zeros, you can just use 1 0 for that hextet to hold that particular hextet place value. You can also, if there are contiguous quad 0 hextets, you can use a double colon to signify those contiguous quad 0 IPv6 hextets. 1, 2, 3, 4, 5 hextets. There should be 8. So if there's 5 holding a place, that tells me there are 3 contiguous quad 0 hextets. The prefix is, we no longer use the slash number or the subnet mask, and with the like a 255.255 decimal subnet mask, but we use the prefix length, and it's generally a /64. What we do, since there's 128 bits in an IPv6 address, typically that's just chopped in half, and the first 4 hextets would belong to the network. The last 4 hextets would belong to the interface ID. So 2001 DB8 A0000 would be the first 4 hextets, and the last 4 hextets would be 4 quad zeros. We went through that really quick. Are there questions, comments? And the gentleman who asked me the question, I don't even know who it was. Was it Adam?
Yes. Yes, I believe it was Adam.
Okay. Adam, can you, if you can enumerate that to me in an email and kind of explain what you're asking, I'll make sure I answer it.
Yeah, no, absolutely. My first question seems so much more academic compared to IPv6, which it blows my mind when I look at it.
Okay, well, IPv6 is actually easier than v4. It's just more numbers. Honestly, anybody, I mean, I cut my teeth on v4, and I know some others in here that did too. And when v6 came out, we all kind of went,
yeah,
and then all of a sudden we got to doing it and realized it.
Like
realized
talking about
that it was.
It just,
I'm sorry.
No, I was just going to say it looks a little crazy looking at it, and I've tried to understand it before, and I get it, I from a formatting standpoint, but like some of the protocols and stuff, I think I'm still grasping.
Well, if you don't, do you have a networking background?
Very, just I'm not like a network engineer by any stretch.
Well, that's okay. You still understand the logic.
I've been in it for years, for 30 plus years. So, I kind of understand it. But IPv6 is another animal for me.
Well, you might want to review that other course. I think that would help you, or we can have a separate session on it if you want to. I think I can clear it up for you. Be happy to do that. Anything else?
I
I'm going to
guess,
stop the recording.
I guess we're assuming